In this video, we're going to look at rational functions again, and we are going to look at end behavior, this is a refresher, and then we're going to get into finding some of the features all at once, and then looking at a graph and how to sketch that on our own. So, for starting with 1 and 2, we have some end behavior problems. So the first thing that I see on this graph is that it's in two pieces for number 1. I have one solid black line in the top right, and then one solid black line in the bottom left. And then I see the dotted lines. So those dotted lines are huge to notice as well. The one that goes up and down, remember, is our vertical asymptote. And vertical asymptotes always use x. In this case, our vertical asymptote is x equals 2. And then the horizontal dotted line, as you would imagine, is our horizontal asymptote. The question is, do we use a vertical asymptote or a horizontal asymptote to find our end behavior? In this case, our horizontal asymptote's at y equals 3, our vertical asymptote's at x equals 2. Our end behavior is always the right and left side of our graph, so we're going to use the part that the left and right side flattens out against, our horizontal asymptote. So for the end behavior, as x goes to negative infinity, that's our left side, that flattens out against 3. Oh, I apologize. It's not an equal sign, it's an arrow. F of x goes to or approaches 3. As x goes to infinity, the right side of our graph, f of x goes to 3 as well. So for end behavior, it's always just your horizontal asymptote. So for number 2, I'm not even going to bother with the vertical asymptote. Since all they want is the end behavior, let's just focus on the horizontal asymptote. That horizontal asymptote here is at y equals 1. So as x goes to the left side, we have f of x approaches 1. And then as x goes to infinity, the right side, f of x approaches 1 as well. They will go to the same thing. They won't go to different numbers there. So that's just a quick refresh on end behavior. Now into the graphing portion. So above the graphing portion, you can see some reminders about what to do with rational functions. Several different things that you're looking for. You're looking for a horizontal asymptote, a vertical asymptote, and its holes. And then your domain is an important feature. And it's always helpful to know our x and y intercepts as well as our end behaviors, the familiar stuff. But let's make a quick note here. If we are simplifying our rational function, that connects to our holes. Simplifying and holes are related because whatever we cancel will produce a hole. So I might even note that holes happen if we simplify. So at this step, you might start thinking, okay, let's look for holes. Then you can move on to vertical, horizontal, and domain. And it's okay to change up this order. If you find a better order that works for you, that's fine. I prefer to start actually in the order that this is listed on the paper that you see here. So domain, vertical asymptote, hole, horizontal asymptote, x, y intercept, and then end behavior. And I might jump around from there to there. E says that you graph this on the graphing calculator. We're just going to give it a quick sketch on our own. If you want to type this into Desmos, feel free to do so. So, number 3 says f of x equals 3x plus 6 over x plus 4. And the domain always comes from our denominator. Take the bottom, set it equal to 0, and then solve. We get x equals negative 4. So that is the number we are not going to keep in our domain. So we write our domain as all real numbers, except x does not equal negative 4. Conveniently, we cannot cancel x plus 4 with any factor in the top because it doesn't match. So that means that we don't have any holes, since nothing canceled, and the only part of our denominator creates the vertical asymptote. Well, we already solved an equation that had x plus 4 in it, so our vertical asymptote is just x equals negative 4. So let's sketch that onto our graph here. We have a vertical asymptote that goes straight down, negative 4. You can put a dot there first if you'd like at negative 4 on the x-axis and then go from there. But there's our vertical asymptote. Awesome. The horizontal asymptote It always comes from looking at the degree, so I'll change to blue here. The degree on the top in comparison to the degree on the bottom will tell us our horizontal asymptote. So let's look. There's a 1 on the x on top, so our degree on top is 1. And there's a 1 as an exponent on the x on the bottom, so our degree on the bottom is also 1. So this is when they match. They're the same. So we need y equals leading coefficient divided by leading coefficient. So my leading coefficients are just the numbers in front. If there's no number in front like there is in the bottom, it's just a 1. So my horizontal asymptote is 3 divided by 1, or just 3. So y equals 3 is our horizontal asymptote here. So let's draw that in as well. Going straight across, touching the y-axis at 3, we have a horizontal asymptote that cuts our graph into 2 pieces. Awesome. So now our x-intercept, we are going to look at just the numerator for this. So 3x plus 6 is our numerator. And we set the numerator equal to 0 to find our x-intercept and solve. So subtract 6, you get 3x equals negative 6, divide by 3, and you get x equals negative 2. But that's not how we write an x-intercept. We always write an x-intercept as an ordered pair. Negative 2, 0. Awesome. And our y-intercept is similar. We're plugging in something for 0, but we're plugging it in for all the x's. So we have y equals 3 times 0 plus 6 over 0 plus 4. Well, if we simplify this, 3 times 0 is just 0. 0 plus 6 is just 6. 0 plus 4 on the bottom is just 4. And 6 divided by 4, that's just 3 halves. So y equals 3 halves is a part of our y-intercept, but once again, we don't put y equals 3 halves. We put 0, comma 3 halves. We put an ordered pair so we know exactly where it is on the graph. So let's actually put those onto the graph. The y-intercept happens on the y-axis. Go to 3 halves. It's about right there. And then our x-intercept is at negative 2, 0. So that's right there. Awesome. I should have done the horizontal asymptote and then gone straight to end behavior. But so end behavior is always something related to horizontal asymptotes for rational functions. So in this case, our horizontal asymptote was 3. So as x goes to negative infinity, f of x goes to 3. The end behavior always matches your horizontal asymptote. And as x goes to positive infinity, f of x goes to 3 again. So let's actually sketch our rational graph here. We have 2 points, and we know that the end behavior, it flattens out on the right side along 3 and the left side along 3. The only other thing we need to know is that those 2 lines don't connect, and they're curves. So let's just do our best guess here. This curves like that on the left side, and the right side's going to go through our red and yellow dots and then curve down. So there's a pretty good guess. If you typed this into Desmos, it would give you a graph that looked a lot like that curve right there. Awesome. So scroll down to number 4 and 5, and we have 2 more examples that we can graph here. I don't necessarily remember all of my colors, so I'm just going to give them different colors this time. Sorry about that. Step 1 was to simplify our rationals, and in this case we have x squared plus x minus 2 over x squared minus 4x plus 3. This will indeed factor and simplify, so let's do that first. X squared plus x minus 2 factors in 2 steps as x plus 2 times x minus 1. And then the bottom will factor in 2 steps as well as x minus 3 times x minus 1. So right there, you can see x minus 1 cancels with x minus 1. Alarm bell should be going off in your head that wholes always come from canceled factors from the denominator. So x minus 1 equal to 0 will make a whole at x equals 1. But that's not how we write a whole. We always write a whole as an ordered pair. There's an x and a y, so we need to find that y value. In order to do so, we need to plug in to our simplified equation. So x plus 2 over x minus 3. So let's do that. F of 1 equals 1 plus 2 over 1 minus 3. 1 plus 2 is 3. 1 minus 3 is negative 2. So our y value is negative 3 halves. So that hole on our graph will look like 1 negative 3 halves. So we are right about here. And I'm just going to put a circle right around that spot. Not a filled in dot, a circle, because our graph does not include that point. It's a hole. So let's go back to our domain. I know I skipped over it before. Domain always comes from, I'm going to do a separate note down here, and I want to do it in a different color than red. Domain always comes from the denominator factors. So I'm going to take x minus 3, set it equal to 0, and I still need that x minus 1 factor. If we solve that, we get x equals 3 and x equals 1 are both numbers that will make zeros in the denominator. So those are issues that we do not want to include in our domain. So we have all the real numbers, but we're not going to include either 1 or 3. The 1 is a whole, but the 3, this part, that's our vertical asymptote. So we've already found our vertical asymptote. It's x equals 3. Whatever's left in your domain, and you can even see it up here, x minus 3 is still in my denominator. Whatever's left there after you simplify will be a vertical asymptote. So let's draw that in. At 3, we have a vertical line that our graph will not touch. So our graph will split right there at x equals 3. Awesome. On to our horizontal asymptote. We have x plus 2 over x minus 3 is what's left. So we're going to use the entire simplified equation to check our degree. The degree on top is 1, and the degree on the bottom is 1. So this is another case where it's the same on the top and the bottom. So we need our ratio of leading coefficients. In this case, both of those leading coefficients are just 1. So our horizontal asymptote will just be y equals 1. So let's go ahead and put that in. Dotted line straight across where y is 1. So that yellow line is our horizontal asymptote. Awesome. I'm running out of space to do the work for my x-intercept and my y-intercept, so I'm going to go ahead and erase the work I did for the domain down here, since we've already filled that in, and then I'll do x and y-intercept down here. Last time I forgot to go from horizontal asymptote straight to the end behavior, but this time I won't forget. So since we found the horizontal asymptote, we should automatically answer our end behavior is the same as our horizontal asymptote. So as the left side goes to infinity, we go to 1, and as the right side goes to infinity, f of x goes to 1 again. So there's your end behavior. Awesome. So the last part is our x and y intercepts. The x-intercept, you always take the top, so all that's left in top is x plus 2, set it equal to 0. X equals negative 2 is the x value for our x-intercept, and 0 is always the y value. For the y-intercept, we plug in 0 for all the x's, so 0 plus 2 over 0 minus 3. Other than at the very beginning and for domain, you only use the simplified equation. It's worth noting that. So don't use x squared plus x minus 2 over x squared minus 4x plus 3 to plug in those zeros. Only use the simplified equation. So we simplify it, we get 2 over negative 3 is our y value, so our y-intercept is negative 2/3 for the y, and then 0 always for the x. Awesome. So let's put those two dots on the graph. We have negative 2, 0 right there is our x-intercept, and 0, negative 2/3 is right there as our y-intercept. So now we have two dots, both horizontal and vertical asymptotes, and a hole. So we just have to make our graph fit into those two pieces. Like you saw above, our graph was in two pieces that were opposite one another. We are going to assume that's true again. So the top right will look like that blue chunk, and the bottom left will look like this chunk, but keep in mind, we don't go through the red circle, we skip over it. So the red circle is a hole, so you skip right over that red hole right there. You do need to go through the intercepts though. If you type this into Desmos, you should get a similar blue curve. Desmos probably won't show you that red hole though, so everything else you would have to know about this graph. Over to our last one, number 5, we have f of x equals 2x over x minus 1. This does not simplify, so I'm just going to go ahead and start by saying there is not a whole. And let's start with our domain. X minus 1 is the only factor in our denominator. We set that equal to 0, and we get that 1 is the issue for our domain. We're not allowed to plug in 1 because that would be dividing by 0. So we have all real numbers except for 1. Consequently, we also have a vertical asymptote at that same spot because domain restrictions are either linked to wholes or vertical asymptotes. Since we couldn't cancel, there was no whole. So let's put x equals 1 as a vertical asymptote. Vertical line right there. And then let's jump over to horizontal asymptotes. Horizontal asymptotes, we always check the degree. On top, we have an exponent of 1. On the bottom, we have an exponent of 1. Those are the same, so we need our leading coefficients. Y equals LC over LC is how we'll find that leading coefficient ratio. So on top, we have a 2. On the bottom, we just have a 1 because there's no number in front of x. So our horizontal asymptote is just y equals 2. So we draw a straight line across that 2. And what that also means, I won't forget it this time, is that our end behavior, as x goes to negative infinity, f of x goes to 2. And as x goes to positive infinity, f of x goes to 2 as well. So end behavior and horizontal asymptotes always match. Down to the last two, in my opinion, some of the easiest parts, the x and y intercept. If you have Desmos, this will show you the x and y intercept, but we can find it by hand as well. So x-intercept, take the top, set it equal to 0. So 2x equals 0, divide by 2, and you get 0 divided by 2 is still 0. So our x-intercept is 0, 0. That means that our y-intercept is also going to be 0, 0. If ever you have a 0, 0 as your x-intercept, it's also your y-intercept. But let's just do the work and prove that. For y-intercept, we always plug in 0 for all the x's, so 2 times 0 over 0 minus 1. That gives us y equals 0 over negative 1. And 0 divided by negative 1 is definitely 0. So that checks out. Our y-intercept is also 0, 0. So here we have our rational with our horizontal and vertical asymptotes. And then we only have one dot to go with. But it's all good. We can still graph this function. It's just going to go up here in the top right. And then right here in the bottom left, and it will not cross over those asymptotes, but it will go through the x and y intercept. So that is just a quick way of how to graph by finding features. Obviously, Desmos will do a nicer job of graphing those for you, and you could copy it from there. But eventually, we will be better at graphing these things by hand by finding all of these unique features like holes, vertical asymptotes, horizontal asymptotes, and so on and so forth.